Hello everyone, my name is Sajad Khodadadian and today I'm going to present you my latest work, Finite Sample Analysis of Two-Time Scale Natural Greedy Actor-Critic Algorithm. This is a joint work with Dr. Thinh Doan, Professor Siva Maguluri and Professor Justin Romberg. Reinforcement learning in recent years has received a lot of wonderful results in a lot of scenarios. For example, in the game of AlphaGo, reinforcement learning algorithm can beat the best human in this game, and also in the virtual situation, reinforcement learning algorithms can learn robots that behave very well and very close to what humans actually do in real world. A reinforcement learning setting can be shown as, or summarized as is shown here. There is an agent in which at each time state k is at some state k, and this agent at this time at time step k take action ak, and based on the state in which the agent is in and the action it takes, the environments return some rewards to the agent, and consequently the agent transfers to a new state, k plus 1. And the goal here is that we are trying to maximize our rewards. However, we have to somehow mathematically explain what we are doing here, and that's where Markov decision process comes to the play. So Markov decision process, the main objective function is in a Markov decision process is value function, which is the function explained or defined here. It's a function of the policy and also some initial distribution rho, in which I'm going to ignore during this presentation since it's constant throughout the whole presentation. Other elements of this objective function is the policy, in which I'm trying to find the best of it, and also the actions. The actions at each time step comes from a distribution, and this distribution is actually this policy. So these actions are actually sampled from this policy in this manner. And also the next state at each time step can be, is being sampled by this transition probability P. So if you are at a state ST and you're taking action AT, with this probability or with this distribution, you transfer to the next state. Also, I denote the rewards in each time step with R, ST and AT. And there is also a discount factor, so that instead of summing up all the rewards, I discount them in order to make sure that V pi does not blow up to infinity. We can also define Q function the same way as we define V function, except that in the expectation, we condition on the first state and the action. Our goal here is to maximize the value function. Since, as I explained before, this value function is an indicator of the reward which we receive throughout the process. So we are trying to maximize the reward, or similarly, we are trying to maximize the value function. One of the algorithms or methods in order to find the optimal policy is the gradient ascent method. In this algorithm, we think of value function as a function from the policy to some scalar, and we try to move towards the gradient of the function, and by this gradient we are trying to update the policy. If the function, if the value function look like a function like this, which is a concave function, and we move towards the gradient, we can be hoping that after a while we're getting close to this optimal policy pi star, which is the peak of this curve. However, the challenges we have is that, first of all, our value function v pi is not a concave function as is drawn here, and also we don't have access to these gradients in each time step. I should mention here that access to this gradients is the main distinction between Markov decision process and reinforcement learning. In Markov decision process, we assume we have access to this gradient, but in the reinforcement learning, we don't, so that we have to somehow estimate these gradients. Okay, so before I go to the estimation and what we do in the reinforcement learning, I explain natural policy gradient, which is another variation of a gradient method. So in order to explain natural policy gradient, I have to explain softmax parameterization of a policy. Each policy, which is a simplex, basically S-dimensional simplex, can be shown or represented with softmax parameterization with some theta vector in the space of R to the power S times A, as is shown here. So basically, this parameterization is a mapping between simplex and R S to the S times A. Having this parameterization, one can update the policy or one can update the thetas by taking gradients with respect to these thetas. However, even if we converge, it can be shown that a lot of times the convergence rate is small because we have so many zigzags. Instead, what people do is that they multiply the gradients with some preconditioner, and we take steps towards this tilted gradient. There are two famous preconditioners. One is Hessian matrix, in which results in the Newton's method in the space of the theta. And also the second one is the Fisher information, in which results in the national policy gradient. All right, all these things that I mentioned here, all is in the space of the theta. However, as I mentioned from the beginning, I'm interested in finding the optimal policy, not the optimal theta. The nice thing about this Fisher information is that if I use this as my preconditioner, the corresponding updates of the policies can be written as an exponential weight update as is written here. The only unknown here in each time step is q pi k, and assuming we have access to the exact q pi k's, it can be shown that these updates, policies of these updates converges to the optimal policy with this rate. This rate is very nice in two senses. First of all, it's 1/k, which is relatively fast, and also it doesn't have any dependence on the state and action. All right, so having this theorem in the previous page, I can basically draw an algorithm in which I have a loop, and in each state of the loop, I calculate q pi k, and then having this q pi k, I update my policy with this update. So, but the problem, as I mentioned before in reinforcement learning, is that I don't have access to the gradients, or similarly, I don't have access to the Q functions. Basically, in reinforcement learning, I don't have access to any of the parameters of the system. So I don't know Q pi k. So what I do is that I have to somehow estimate the Q of Q pi k. And this estimation should be in a way that I can actually implement in real world. So this algorithm, which I denote by 2-time scale natural greedy actor-critic, is a real world practical algorithm for implementation in real world. So what I do is that at each time step, I take one sample of state, action, and reward by following policy pi hat k, where I'm going to update later. And using this single sample, I update my Q table, which I'm keeping track of throughout the whole algorithm. And using this Q table, I update my policy at each time step. And also using this policy and convex combination of this policy with the uniform, I find the pi hat k. So this algorithm is completely practical because it doesn't require any access to reward function, transition probabilities, or anything like that. This just simply requires interaction with the environment. You sample, you basically perform some action, and the environment goes to the, makes you go to the next state and gives you some reward. So everything is practical here. However, the problem is that we don't know if it's converging or not. Our main contribution here is that we show under single assumption of the Unichain, and with these step sizes, there always exists epsilon small enough such that if you set epsilon k equal to epsilon, you converge with rate of 1 over k to the power 1/4. Furthermore, if you want global convergence without fixing an epsilon, you can choose these step sizes, and you can basically converge with 1 over k to the power 1/6. Notice that here we only impose one single assumption, which is a Unichain assumption. In our analysis, we have several difficulties. One is the intervened difficulties of having updates at 2 time scale. Alpha k and beta k are different step sizes. We have asynchronous nature of the Q table update. And we have also Markovian randomness. This pi hat k is time varying and also Markovian. The noise that is imposed by this pi hat k is Markovian. Regarding the assumption, as I mentioned before, we need only Unichain assumption. What is Unichain assumption? Unichain assumption basically enforces the underlying Markov decision process to be connected, the states of this MDP to be connected under all the policies. For example, this is a Markov decision process which is not a Unichain. Because under policy which I perform A1 all the time, S1 and S2 are completely disconnected. So this is the only assumption we are imposing here. And it can be shown that this is actually necessary. Compared to the other works, our main contribution here is that we are getting rid of this, the assumption they are making. One of the assumptions they have is that they assume 1 over pi t for all the t's and actions and states. This is bounded with some constant b. However, we know that this assumption cannot be satisfied in reality, or at least a lot of time this assumption cannot be satisfied, because we know that this pi t might converge to the 0, and this 1 over pi t can blow up to infinity. And as a result, this condition might be not be able to be satisfied. So our main contribution is that we are getting rid of this assumption and we are just imposing single assumption of the Unichain. Notice that in those works, they converge, they have almost the same rate as we have here, but we don't have any other assumptions. Thank you for your attention.